day, students. We are going through the matrix methods in ray optics. We have seen how to represent the translation of a light ray and the refraction of a light ray in matrix form. Let us just review it. The matrix form of translation is represented as matrix T, given by 1, 0, d by mu 1, where d is the distance traveled in the z-axis and mu is the refractive index of the medium through which light is traveling. Matrix representing refraction of light is given by matrix R, 1 minus P, 0, 1, where P is the power of the refracting surface, mathematically given as mu2 minus mu1 divided by R, where mu1 is the refractive index of the first medium, mu2 is the refractive index of the second medium, and R is the radius of curvature of the refracting surface. So light can undergo these basic operations whenever it travels through different mediums of refractive indices. We consider some such mediums here. Here I have shown you some types of lenses. The first one is a double convex lens of short focal length range. The second one is again a double convex lens of long focal length range. And again, the third one is a lens having concave and convex sides. Now, when light travels through all these different optical components, it will undergo translation and refraction. So, in order to find the resultant ray, we will have to mathematically do a lot of calculations for each ray at each point of operation, what all undergoes. When light passes through different optical components, it undergoes a lot of translations and refractions. In here, we can see that light can be incident on the first refracting surface of the first lens, then it translates through it, and again refracts through the second surface of the first lens. Then it translates towards the second lens, where it again undergoes refraction at the first surface. It translates through it and refracts through the second surface. And again, it translates towards the third lens. And at the point of contact, it refracts into the lens, travels through the lens, and then at the second surface of the third lens, it refracts and emerges out of the system. So we see that a number of translations and refractions have taken place here. We can sum all these operations together and use a single operation to represent it. Okay, so here I can use a single box to represent the whole operations taking place within. I need not know what happens within the system. Okay, so for that, first I see an incident ray falling on the black box. I call it black because I don't know what is happening. So I see a light incident upon a black box, and it produces some effect upon the incident ray to produce, and we call the black box the system matrix. The system matrix performs some operation upon the incident ray to produce the emergent ray. Okay, so I can represent it in the form of a matrix equation as shown here. If the ray coordinates of the incident ray is lambda1 x1 and the ray coordinates of the emergent ray is column vector lambda2 x2, I can write the emergent ray lambda2 x2 is equal to the operation of a system matrix upon lambda1 x1, and the system matrix shown here is B minus A minus D C. I have used these alphabets because system matrix is represented using Gauss constants, and these A, B, C, D constants are called Gauss constants. Now let us first derive the system matrix for an optical component. Something is placed in the XZ plane. The Z is the direction of propagation of light. And some optical component is placed in this plane. Okay, so for us, we need not know what it is, but to derive the matrix, I'm going to show what the optical component is. Okay, we have selected a double convex lens of refractive index mu. Okay, now light is made to fall upon it. So on the first refracting surface, at point A, light will undergo the first operation, refraction. After it refracts, it travels through the lens, that is through a homogeneous medium, so it translates through the lens to the point B. So it undergoes the second operation, translation. And at point B, it is a surface of or the boundary between two different media. It will undergo the second refraction. Okay. So in this optical component, light undergoes three basic operations: refraction at the first surface, translation through the lens, and refraction at the second surface. So let us represent the incident ray as the ray vector lambda1 x1. At the point A, light undergoes refraction, right? And after refraction, let the ray coordinates be defined by lambda1 prime, x1 prime. Light then translates from the point A to B. It undergoes translation. And at B, let the ray coordinates be defined as lambda2 prime, x2 prime. And at B, light undergoes the second refraction, and after refraction, let the ray coordinates be lambda2, x2. Okay. Now I'm going to write the mathematical form for all these operations. So at A, after refraction, I can write the ray coordinates lambda1 prime, x1 prime is equal to the refraction matrix at the first surface upon the incident ray lambda1 x1. Right. Now when light translates from point A to B, I can write the ray coordinate at B lambda2 prime x2 prime is equal to translation matrix upon lambda1 prime x1 prime. Okay. Now for the third operation at B, you have the second refraction. I can write the emergent ray lambda2 x2 is equal to refraction matrix at the second surface R2 upon lambda2 prime x2 prime. Right. Now for this vector, I'm going to substitute this equation. Hence I get matrix R2 into T matrix into lambda1 prime x1 prime. Okay. Now for lambda 1 prime x1 prime, I can substitute the first equation, that is matrix R2 product matrix T product matrix R1 into lambda 1 x1. The translation matrix can be written again thus. We see that the product form matrix R2 product matrix T product matrix R1 gives the matrix form of this lens. Hence I can write the system matrix of a lens is given as product of R2 into T into R1. We have to observe the order of multiplication. It is in the reverse order that the product has to be taken. Okay, so in the next slide, let me rewrite the system matrix. S is equal to R2 upon T upon R1. I'm going to expand these matrices. R2 can be written as 1 minus P2 0 1. T can be written as 1 0 d by mu 1, and R1 can be written as 1 minus P1 0 1. This is equal to, taking product form, I can write 1 minus P2 d by mu, that is these two terms plus these two terms. Then the second term becomes these two terms plus these two terms, that is minus P2. This term, the A21 term becomes these two terms plus these two terms, that is d by mu. The last term is 1. Product over 1 minus P1 0 1. Again, this can be written as system matrix will be given as 1 minus P2d by mu. We have minus P2 plus P1 P2 d divided by mu minus P1 d by mu, then minus P1 d by mu plus 1. Okay, so this is the system matrix. Thus we can write lambda 2 x2 in matrix form is given as system matrix upon lambda 1 x1, where the system matrix is given of the form 1 minus P2 d by mu minus of P1 plus P2 minus P1 P2 d by mu and 1 minus P1 d by mu. Okay. In Gauss constants, system matrix can be written as B minus A minus DC. This implies A is equal to P1 plus P2 minus P1 P2 D by mu. B is equal to 1 minus P2D by mu. C is equal to 1 minus P1D by mu, and D is equal to minus capital D by mu. Here, P1 is given as mu2 minus mu1 by R1. P2 is given as mu1 minus mu2 by R2. D is the distance traveled by the light ray within the lens in the z-axis, and mu is the refractive index of the lens. So here we see that the lens is placed, let us assume that it is placed in a medium of refractive index mu1. So while doing problems, this will be substituted as mu2 minus mu1 by R1 becomes mu minus mu1 by R1. Okay. And P2 becomes, yes, mu1 minus mu by R2. Again, while doing problems, you should use lens convection while substituting values for R1 and R2. That is, R1 is usually negative and R2 is positive. The system matrix also has a particular property that the determinant of system matrix will be 1. This implies that BC minus AD is equal to 1. This is a relation between the Gauss constants. That's all for today. Thank you.